series in just a minute. We do have a tight schedule today, so due to those constraints, to better get to your questions, please type them into the chat and the staff will get to them as soon as they can. Now, also do not forget, you can also email those questions as well. If we run out of time to answer them verbally after each presentation, we will try and get to them at the end of the module if you want to stick around for that. Here's part one of today's agenda for Module 3. Today we'll be tying into what was presented in the two prior modules and apply that information to reviewing projects. We have how to review a project 1, which will be presented by Anthony Vroblick along with myself. And then we have how to review a project 2, which will be presented by Changyi Wu. After the how to review a project presentations, there will be a presentation from Lisa Schaefer on groundwater mounding, along with examples of performing the analysis that is required. After that, we will have quiz 3. Again, please give it your best shot so that we can grade ourselves on how well we cover the material. You will be completing the quiz online during the time allotted. After that, we'll review the quiz answers and, like I said earlier, take any unanswered questions for the material covered in the module as time permits. So let's get started. Like I said, I, along with Anthony Vroblick, who will take over in the second half of this presentation, are going to go through part 1 of how to review a project. This presentation came about because our review of approved projects during compliance audits showed that projects were being approved even though the calculations and stormwater management reports submitted for local approvals did not comply with the stormwater management rules and the local stormwater control ordinances. Therefore, should these projects fail, the municipalities involved would be in violation of their respective permits. Here are the goals of this presentation, which are by no coincidence the goals of a successful project review. We want reviewers to be able to identify the design and performance standards that must be met on site, review applications for compliance with green infrastructure, stormwater quantity, stormwater quality, groundwater recharge standards, and review BMPs for compliance with the design criteria in the BMP manual. The information required in the stormwater report is specified in the stormwater control ordinance, and checklists are available to help with the review. The reviewer must make sure that any information found missing from the report must be added before approval of the project. The checklist found at this link in the Tier A guidance document here on the slide can help with your review of the report and help to just organize your observations and comments. This presentation is laid out to follow along with the checklist. Now we're going to look at what the reviewer needs to be looking for in the stormwater management report. The first step in the project review is to check if the application package is complete. All the items listed here must be part of the application. Pre- and post-site and grading plans are essential, as are the associated calculations and any drainage area maps. The details in the report section should match up with the information on all plan pages. Too often we find that some parts or even all of the stormwater report do not match the site and grading plans because the report was copied from another project. So the reviewer must also be aware of whether or not the permittee has a more stringent standard of what must be in an application for approval. If so, the reviewer should be looking at all that information. The township's adopted ordinance posted online is also a great starting place to find what information is required to be submitted. The township should have adopted the March 2nd, 2021 amended rules by now. Another issue we see that should be checked right away is that the plans and reports should also be reflected in the maintenance plan so that the BMPs will continue to function as designed. Too often we see maintenance plans submitted that were copied from other projects and they don't even match at all the project that was submitted. So like I just said, it is important that the reviewer checks that the site description matches up with the plans. The drainage and discharge points all need to be checked along with any change in pervious or impervious coverage. That includes regulated impervious surface and regulated motor vehicle surface for each sub-drainage area. And then also soil information for the site should be included and accurate. Changyi covered the use of web soil survey as a means for getting your soil information, and he will also provide additional guidance later on today. As a side note, print versions of county soil surveys, they're not always up to date and they're not really recommended to be used. The report must include the following information regarding design and performance standards when it comes to what's required, along with any applicable variances, waivers, or exemptions, and how the standards will be met. Again, we find that this is often missing, or again, does not even match up with what is on the plan. So this is very important that this information is provided. The reviewer must be sure that the following calculations are included in the report. Time of concentration, as discussed in Module 2 by Lisa, is essential to characterizing a site. Time of concentration must be calculated and included in the report. Some permittees may require this information be submitted on a CD so that it can be checked and verified. No matter the format, it is important to include all of this information, including storm routings, hydrographs, the groundwater recharge spreadsheet, the mounding analysis if it's applicable, and water quality calculations, and make sure it matches what's on the plans. You saw this slide earlier in Module 1 in the overview presentation. You always should check whether the project meets the definition of major development, because there could be the chance that it doesn't. Also be sure to also check the permittee's definition of major development, as it may be stricter than the department standard. To find the permittee's definition of major development, the reviewer should check the permittee's ordinances. We'll note here though, you need to distinguish the different types of surfaces, whether it be regulated motor vehicle surface, regulated impervious surface, or other pervious surface, and etc. in the report. There are one or more major development thresholds that may apply to the project that the reviewer should be aware of, including the residential site improvement standards, the permittee's stormwater control ordinance, and the NJDP land use regulations. As you see here, each one of them has their own definition. Once the reviewer has verified that the required information has been submitted and is accurate, they can begin to actually review the design and performance standards. The plans and a report must address the information listed here. This information is crucial to determining whether the project was designed properly. Information such as whether the project is discharging to a flood hazard area or a Category 1 waterway are often not included and therefore even overlooked during the review. This information may also determine whether or not the project requires input from other agencies such as NJDEP Land Use or even the Pinelands Commission. Under the current rules, a reviewer must ensure the proposed design complies with the design criteria established in the BMP manual, which in turn ensures the design meets the design and performance standards of the rules. If something is an alternative design or method of calculation, the department must be notified of the approval. Along with the other standards, reviewers must ensure the BMPs follow the green infrastructure standards, and for this, the BMP manual provides the design criteria and considerations for the individual types of green infrastructure BMPs. Our stormwater audits have shown that many approved projects generally do not comply with the design standards. Whether these errors were missed by mistake or the reviewer waived the requirements, we are not sure, but we have found far too many errors to this point. If the reviewer did allow for waivers or variances, they must be sure that they are applicable. Can waivers or variances even be granted? It's really not a straightforward answer though, and to rectify this somewhat gray area, it is better defined in the new rules. The amendments to 7:8-4.6 were made to clarify the conditions that would warrant the granting of a variance by a municipality for a major development project. The amendments are intended to ensure that municipalities are not granting variances under inappropriate circumstances. Municipalities do not have to grant variances, and they do not have to create a mitigation plan if they do not intend to grant variances. Where a municipality does intend to use the authority to grant variances, it can create a mitigation plan that allows the evaluation of mitigation projects suggested by applicants, thus allowing for the consideration of projects submitted by applicants as is permitted at 7:8-4.6a. To eliminate any potential misconception that a variance is an exemption from attaining stormwater management standards, the word exemption was removed from section 4.6 as part of the rule amendment. With the amended version of the rules, the ability to grant variances requires a bit more effort by the applicant. Now, there must be a demonstration that it is technically impracticable to meet one or more of the design standards. The only allowable variances are for engineering, environmental, or safety reasons, and they have to be spelled out very clearly. Cost cannot really be a factor here. The old low impact development checklist often included statements that something was not economically feasible, and yet cost information was not even formally reviewed. Previously, there may have been a site-wide variance allowed, but now the rule located at 7:8-4.6 states a municipality's approval of a variance shall apply to an individual drainage area and design and performance standard and shall not apply to an entire site or project, unless an applicant provides the required analysis for each drainage area within the site and each design and performance standard. There's a lot more to the mitigation requirements that must be met to obtain approval of a variance in the amended version of the rules. Mitigation must be part of the municipal stormwater management plan and follow these new requirements. It must be selected from the municipal list of mitigation projects, or it could be proposed by the applicant if it meets the criteria for the municipal mitigation plan. It must be approved no later than the preliminary or final site plan approval, must be located in the same HUC 14, must be constructed concurrently or prior to the major development. It must meet the GI standards, and the entity assuming the responsibility of maintenance for the project must submit a written agreement to the review agency. Lastly, the approved variance must now be submitted to the county review agency and the DEP within 30 days of approval. Mitigation is required to receive a variance from the green infrastructure standards, but be aware that certain BMPs cannot be used as mitigation measures and that there are minimum sizing and drainage area limitations. Note that vegetative filter strips and grass swales are excluded as mitigation measures, and they don't address quantity control and groundwater recharge. Green infrastructure BMPs that are used for mitigation need to be sized to manage the water quality design storm at a minimum, and they are subject to the specified drainage area limitations. Variances from the other standards are as shown on this slide. If variance is from groundwater recharge standards, mitigation project must equal or exceed the groundwater recharge deficit. If a variance is for stormwater runoff quality standards, the mitigation project must provide sufficient TSS removal to equal or exceed the deficit resulting from the variance. Or if the variance is for stormwater runoff quantity standards, the mitigation project must provide equivalent peak flow rate attenuation upstream and discharge the same water course. Note, there is no waiver or variance allowed for groundwater mounding. That's because the steps listed in Chapter 13 of the BMP manual make it very clear that if the selected BMP fails to pass the groundwater mounding analysis, another BMP must be selected and assessed, meaning that a redesign is required. The reviewer should also be able to determine whether linear development exemptions exist on the site. The following linear development exemptions may be granted if the requirements are met for each. That is the construction of an underground utility line if revegetated upon completion, the construction of an above ground utility line if existing conditions are maintained to the maximum extent practicable, or the construction of a public pedestrian access if made of permeable materials and no greater than 14 feet wide. Finally, the reviewer may also allow waivers to be granted for the enlargement of a road or a railroad, or the construction or enlargement of a public pedestrian access if the requirements here are met. They are as follows: public need for a project that can't be met another way, design and performance standards met to the maximum extent practicable. Meeting these standards would require condemning existing in-use structures, where the applicant does not have and cannot get rights to other lands for mitigation. These specific exemptions were discussed earlier in Module 1. Water quantity is exempt if it's in a tidal flood hazard area and flooding will not increase. Water quality is exempt if the site has an NGPD's permit with specific effluent limit, and the groundwater recharge is exempt for previously developed areas in an urban redevelopment area. The last one will also be discussed in part 2 of how to review a project in a bit. So I'm not going to get into depth with this, but the reviewer has to be aware of them. It is important that the reviewer is aware of what urban redevelopment exemptions are and where they can be applied. Urban redevelopment exemptions can only be granted to previously developed areas of a site. The existence of woody vegetation is a telltale sign of whether the exemption can be granted. If the reviewer finds that woody vegetation has returned to areas of a previously developed site, the exemption may no longer be allowed. Removing woody vegetation, putting new construction over this portion of the site will result in a loss of groundwater recharge, so that's why. The reviewer can check the NJ GeoWeb to determine whether the rest of this information is applicable for the site. So in summary, the following are the possible variances, exemptions, and waivers that may be applicable to the site, but it's also important that the reviewer takes the time to make sure that they can be applied and that they are only applied to these specific portions of the site that meet these specific requirements. The next thing the reviewer should be looking at is if the applicant is meeting the design and performance standards using green infrastructure. The current rules require that the design performance standards are to be met using green infrastructure. The rules, they require that green infrastructure BMPs be used to address the requirements for groundwater recharge, stormwater runoff quantity control, and stormwater runoff quality. Subsection 5.2 of the rules includes 3 tables, and they list the BMPs that may be used to meet the design and performance standards. The tables found there, they specify information on how each BMP may be used. Table 5.1 coincides with Chapter 9 of the BMP manual, which are the GI BMPs. They include cisterns, dry wells, grass swales, green roofs, manufactured treatment devices that are green infrastructure devices, pervious paving systems, small-scale bioretention systems, small-scale infiltration basins, small-scale sand filters that are green infrastructure, and vegetative filter strips. Some of the BMPs, they cannot receive runoff from motor vehicle surfaces, and therefore they do not address water quality, like cisterns and green roofs here. Others, they do not attenuate the discharge of stormwater runoff for the 2, 10, and 100-year design storms, so they cannot meet the quantity control requirement, such as a dry well. And I emphasized it about 10 sequences ago, but not all MTDs are considered green infrastructure. but the ones that are, they are included in Chapter 9. These MTDs, they have a vegetative or soil component that meet the green infrastructure definition. Lastly, these small-scale systems listed here, they have a limited drainage area that they can treat compared to other BMPs. So let's take a look at that. As you can see, the column on the left here, it includes the name of the BMP, and the column on the right, it includes the maximum contributory drainage area. So for example, if you're using a dry well, the maximum drainage area would be 1 acre. MTDs would be 2.5 acres, and so on and so forth. Note, this is Table 5.1, so we are only talking about MTDs approved for green infrastructure. Chapter 10 BMPs, they can be used to address stormwater runoff quantity control. These BMPs can have contributory drainage areas that are larger than the drainage areas of BMPs listed in Chapter 9. Chapter 10 BMPs, they include the large-scale bioretention systems, large-scale infiltration basins, large-scale sand filters that are GI, standard construction wetlands, and green infrastructure wet ponds. These BMPs may only be used to meet water quality and recharge if a waiver or variance is granted, so that is very key to keep in mind. BMPs in Chapter 11 are non-green infrastructure, and they always require waiver or variance before they can be used. It is not anticipated that these BMPs will be used much in the future because of what is required in order to grant a waiver or approve a variance. So, as for some of these BMPs noted on this table, blue roofs don't have a reuse component, and extended detention basins are typically large and require additional treatment to meet water quality standards. The majority of the MTDs currently do not have a soil or vegetative component, so they're going to fall here in Chapter 11. And then you see non-GI sand filters, subsurface gravel wetlands, and non-GI wet ponds to round out the rest of Chapter 11 here. The next thing the reviewer needs to look at is the stormwater runoff quantity. Water quantity impacts must be addressed to not only prevent increased flooding due to development, but also to avoid increased flow rates, which can significantly degrade water bodies downstream from a site. In Module 1, Anthony, he covered the different options a designer may choose to follow. I'm going to briefly go through the options to meet water quantity, as we have found this to be done incorrectly in most of our audits. It is important to note that the reviewer must make sure that all points of discharge from the site must meet the water quantity standard, and if not, the project, it's not going to be compliant. So let's begin with taking a look at topography. Why is it even needed, right? Topography, it's important in identifying where the stormwater flows and is required to determine drainage areas and the time of concentration. The reviewer should be able to find the topography information on the plans and make sure that it's accurate. This may require the reviewer to physically see the site as well, though. It's often difficult for us to find drainage maps in these stormwater reports. We also see situations where the drainage calculations in the reports do not match up with the drainage maps in the plans. So we need to see existing and proposed contours and the point of analysis along with TC flow paths and the drainage area to each point of analysis. The reviewer must be sure that the data used in the calculations matches the various maps and plans. This information must also be included on the drainage plans. It's very important to understand that each drainage area needs to be calculated separately. The reviewer should see the following calculated separately for each drainage area and must check the calculations for each drainage area. It cannot be assumed that if one calculation is correct, then the rest are correct as well. So as you see here on this example site, the flow was evaluated and sheet flow directed primarily in a southerly direction here. However, we received complaints of flooding along the road lying to the east of the project and from the area northwest of the project. So it was determined that the drainage areas were not delineated correctly. Whether or not that was due to an incorrect evaluation of the topography is unknown, but this shows why it's important to properly evaluate it and delineate drainage areas. To prevent those issues from occurring, the reviewer must verify that all drainage areas are outlined correctly and the proper time of concentration flow path is used. You also got to make sure the time of concentration is even calculated properly to begin with. So the reviewer, they need to make sure that any natural ponding on site is included in the model. This is often overlooked by the reviewer, and ignoring it for the existing condition means the allowed proposed volumes will be larger than they actually should be. We will look at depression areas more in a bit. So on the same example site that was shown before, there was a 6-inch deep ponded area within the shape depicted. This was ignored, and the basin was made significantly larger than what was needed. If there are any questions as to whether areas of ponding exist on site and it cannot be determined from the photos of the site, it may be necessary for the reviewer to again go and visit the site in person. The reviewer should be checking land cover next. Land cover should be clearly marked on the plans and be specific to what the land actually is. It should also include any existing BMPs that were on site. The reviewer must verify that the plans and cover descriptions in the report match what is actually on the site. Aerial photos can be used to make sure the most pervious cover that existed in the past 5 years has been used in the calculations. Again, it may be necessary for the reviewer to verify land cover conditions in person to make sure that they have been accurately described. Changi has gone through how to determine soils last Thursday, but just to reiterate, it's important to make an accurate determination of the soil types on site. This type of soil greatly affects the functionality of the BMP. Again, the reviewer can find soil info at the NRCS Web Soil Survey webpage at the link provided here on this slide. If information on the site soils cannot be found, you can use methods found in Chapter 12 to determine the hydrologic soil group, either from the default HSG method or even from soil testing. Making sure that the soil data for the site is accurate, it's a very critical part of the review process. Inaccurate soil information can make or break a stormwater BMP. So a good practice to keep in mind is review the soil testing first before anything. As stated earlier, the review checklist, it's an excellent guide for assisting one to review these major development projects. Here are a couple of items that we need to take a look at when we review projects. So we need to make sure that the Manning sheet flow roughness coefficient, it's 0.4 or less for the TC calculations. According to the NRCS, the maximum roughness coefficient to be used is 0.8 for woods with dense underbrush. However, in New Jersey, we do not have that situation, and the maximum coefficient for sheet flow that may be used is 0.4. Lisa covered this in Module 2, and more on this is found in Chapter 5 of the BMP manual. We also need to determine if the TC is in the pre-construction is appropriately calculated. We need to make sure that they are not underestimated. The reviewer should look at time of concentration. Information on how to calculate it can be again found in Chapter 5 of the BMP manual and the National Engineering Handbook. Look back through the handouts for the calculations presentation for Module 2 for more information on the correct way to calculate time of concentration. In summary, the reviewer must make sure that the sheet flow, shallow concentrated flow, and the channel flow inputs are correct. They must make sure that the proper time of concentration was used with the corresponding method. They must check the pre-construction time of concentration calculations, and the reviewer must check the post-construction calculations as well. Next on the review checklist is to identify if runoff from impervious and pervious surfaces are calculated separately and not with a weighted average curve number. We need to make sure that the curve number selection is appropriate of the land cover, and if the rational method is used, the runoff coefficient makes sense. If you recall from Module 2, the acceptable methods of water quantity calculations are the rational method and the NRCS method. The reviewer should make sure that one of these two methods is used for the stormwater report. Just a quick note though, if you do use the rational method, the maximum drainage area is 20 acres. Curve numbers and runoff coefficients are used to calculate the amount of runoff caused by a specific amount of precipitation. As you see here, curve numbers coincide with the NRCS method, and runoff coefficients, they coincide with the rational/modified rational method. The reviewer must be sure that the curve numbers or runoff coefficients correspond with each specific area based on land cover and hydrologic soil groups. Both of these must always be based on good hydrologic condition. Again, this was covered in Module 2. Here's an example of what a land cover table might look like from an engineering report. The reviewer must check these numbers and land cover types against what is shown on the plans. Sometimes you could see that they may not even match up. You need to make sure this corresponds to the plans you see. In all, the reviewer must check that curve numbers and runoff coefficients are justified in the report. The reviewer can verify these in the National Engineering Handbook for curve numbers and Chapter 5 of the BMP Manual for runoff coefficients. The reviewer is responsible for making sure the chosen values are reasonable and accurate as well. Now I will hand it off to Anthony Roblick, who will take you through runoff routing. Anthony?
Okay, just a sec, let me pull this up. Okay, can everyone see this?
Yep, you're good.
All right, great. Thanks, Manesh. So picking up right where Manesh left off, when routing stormwater runoff, routing programs may require unchecking a box to separately calculate runoff from pervious and impervious areas. It's the reviewer's job to make sure that this has occurred and that the areas are routed separately. This can be verified by confirming that the printouts provided do not show a composite curve number, and the reviewer must also be sure that a weighted average of pervious and impervious areas was not used. If an off-site discharge point or point of analysis receives runoff from several sub-drainage areas, the peak flow rate at the discharge point cannot be an arithmetic sum of the peak flow rates from each sub-drainage area. The hydrographs from each sub-drainage area should be combined to find the peak flow rate at the discharge point. So one situation that we often do not see correctly addressed is depression storage. The reviewer should identify if any depression storage areas exist on site and that they are included in the model. Depressions can provide stormwater management benefits and should be protected if possible. One problem that arises from ignoring depression storage in the pre-development condition is that it is not possible to accurately calculate time of concentration. The reviewer must make sure that the depression storage is being modeled as an existing basin in existing conditions. In general, this is the procedure to follow when reviewing existing condition depression storage somewhere within the confines of a proposed development. The reviewer must make sure that the depression area is modeled, the time of concentration is calculated from the outlet of the depression to the point of interest correctly, and lag the depression outflow hydrograph by the calculated time of concentration, and finally calculate the time of concentration for the remaining area of the site and route it separately. So this is the one example of depression storage that was shown earlier. Had the reviewer conducted a proper review of the existing depression storage area, there most likely wouldn't be the issues that are there today. So the reviewer must review the time of concentration to the depression area, calculate the stage storage data for the depression area, model the outlet from the depression area as a weir, and route the contributory drainage area to the depression area. So this is an example of a depression storage modeled in HydroCAD. So the contributory drainage area is routed to the depression, and the reviewer can input the parameters into HydroCAD to make sure that the depression area was calculated correctly. In this case, the depression is modeled as a small detention structure discharging over a 22-foot long broad-crested weir. The lowest elevation is 49.1 feet, and the highest is 49.7 feet. All of this information is taken from the site conditions. The reviewer should check if the rainfall depth parameters are correct for the site and that the appropriate rainfall distribution is used. The rainfall depth and intensity information should come from these sources. So NRCS has developed distributions for New Jersey, including the NOAA C and D distribution, which the BMP manual requires use of. These are already built into many stormwater modeling programs, such as HydroCAD, and the reviewer should check that the correct distribution is selected dependent on where the site is located within the state. Chapter 5 of the BMP manual includes an example of using the modified rational method. The reviewer must make sure that the report shows critical storage volume calculations and detention basin designs must be based on a storm event that results in critical storage volume. Next, the reviewer should identify if the appropriate hydrograph type is used. So the first bullet of this next slide actually needs reads a little incorrectly, so I wanted to clarify this. And if you are following along taking notes with these presentations, you might want to take note of this. When reviewing NRCS method calculations, the SCS unit hydrograph should only really be used outside of the coastal plain area of the state, except in very rare cases where the design engineer can prove that the conditions that characterize the use of the Delmarva hydrograph are in no way present on a site within the coastal plain, or use of the Delmarva hydrograph is not permitted, such as like when sizing an MTD. Other than those cases, though, the SCS unit hydrograph should not be used within the coastal plain. And correspondingly, the Delmarva hydrograph should always be used for sites within the coastal plain area, and use of the Delmarva hydrograph is actually only acceptable within the coastal plain. So that's the clarification. But no matter where you are in the state and which hydrograph is being used, the reviewer must make sure that the same hydrograph is used for both the pre and post conditions. So after having checked the input parameters, we should review compliance with the stormwater runoff quantity standard. Option 1 is almost exclusively used for redevelopment. The revised BMP manual chapter 5 includes a discussion and example illustrating this. As mentioned in module 1, in order to meet option 1, the post-construction hydrograph cannot exceed at any point in time the pre-construction hydrograph. And so here's an example of a post-construction hydrograph exceeding the pre-construction hydrograph. And at first glance, the difference appears to be negligible. However, the rules do not permit any exceedance. And if we were to zoom in, starting at 11.91 hours, we would see that the post-construction hydrograph does exceed the pre-construction. So when we look into the comparison of the hydrograph from the previous slide, we can see that multiple values from the post-construction hydrograph do exceed the pre-construction. Although the peak flow rate of the post-construction hydrograph is less than pre-construction, the shorter time of concentration under the post-construction condition results in this exceedance. We will not be covering option 2 as that was previously covered, and skip ahead on to option 3. So option 3 is the most commonly used, and although that doesn't mean that we don't see many errors in the way it is used, this option requires use of stormwater BMPs with a detention function and outlet control structure to attenuate flow. So here's a list of various Chapter 9 and 10 BMPs that can provide detention. Note that these BMPs are considered GI, which are required to be used to meet the stormwater runoff quantity control standard. And note that Chapter 11 BMPs, which are not listed here, would only be eligible to meet the stormwater runoff quantity requirement if a waiver or variance from NJAC 7:8-5.3 was granted. As we mentioned earlier, the report shall provide routing calculations of all design storms for every sub-drainage area. The reviewer should check that pervious and impervious surfaces are separately calculated, check the NOAA rainfall distributions, and check runoff depth. The report shall provide routing calculations of all design storms and for each sub-drainage area. An example routing calculation can be seen here. So on the printout, it shows exfiltration is included in the routing calculation and is denoted as discarded runoff. Note that this BMP design does not infiltrate the entire 100-year storm into the subsoil. And as you can see on the slide, primary means the discharge of the 100-year storm through an outlet structure, such as an orifice or weir. Infiltration of the entire 210 or 100-year storm is allowed only when the existing site conditions are such that no runoff leaves the site for the pre-construction condition scenario, thereby constraining the design to infiltrate 100% of the volume produced by the post-construction condition for the same design storm. In this case, the maximum storm that can be entirely infiltrated is the largest storm event with no runoff leaving the site in the pre-construction condition. Or the volume of stormwater runoff to be fully infiltrated is required by law or rule implemented by the Pinelands Commission, the Highlands Council, or any other stormwater review agency with jurisdiction over the project. The reviewer must check groundwater mounding analysis for any BMPs that infiltrate runoff into the subsoil. If there's no groundwater mounding analysis in the submitted report, the reviewer shall ask the design engineer to provide it. Often the groundwater mounding analysis will show the mounding as rising above the bottom of the BMP, which means that the runoff discarded through the basin bottom into the subsoil is reduced from what is assumed in the routing calculation. If this is the case, the routing calculation must be adjusted to use a smaller exfiltration rate, which will result in more flow being discharged through the outlet control structure. If more flow is discharged from the outlet control structure, you should check if the peak flow rate from the BMP is still below the maximum allowable peak flow rate. If the discharge flow rate is above the allowable peak flow rate, then the basin size or the outlet control structure may need to be adjusted to provide more storage volume during the design storm. So the next section, the reviewer should check is stormwater runoff quality. The stormwater runoff quality requirements are shown here. For new development, the proposed design must remove 80% of total suspended solids and stormwater runoff generated from the water quality design storm from the net increase of motor vehicle surface. And although there is no numerical target, the reviewer must ensure that the design removes nutrients to the maximum extent feasible. The threshold for the water quality requirement is a 1/4 acre net increase in regulated motor vehicle surface. Each individual drainage area must meet the 80% requirement unless there is convergence prior to discharge from the site. Drainage areas discharging to different locations cannot be averaged together, and additionally, water discharging within a riparian zone must reduce TSS by 95%. Regulated motor vehicle surface can mean more than just a brand new parking lot. It also includes pervious areas that are intended to be used by motor vehicles. Additionally, motor vehicle surface that is currently receiving water quality treatment by vegetation or soil, by an existing stormwater management measure, or by treatment at a wastewater treatment plant where the water quality treatment will be modified or removed, is also considered a regulated motor vehicle surface. The reviewer must make sure that the pervious paving areas are treated as regulated motor vehicle surface when considering stormwater quality, although pervious paving areas designed in accordance with the BMP manual can assist in providing the required TSS removal. Runoff generated by a rooftop is considered clean because it is not typically a significant source of TSS. However, it can be a significant source of nutrients, which the reviewer should make sure is considered in the design. Because of this, pretreatment of rooftop runoff may be a requirement depending on the BMP used, and the reviewer should consult the BMP manual for pretreatment information. In the previous modules, we talked about the water quality design storm, which is unique to New Jersey. It's the storm that introduces TSS into our collection systems and waterways. It's nonlinear in its distribution, and it's fairly intense. Here's a graph depicting the total rainfall from the water quality design storm versus time. And here is the graph depicting the rainfall intensity duration curve. When you look at the intensity duration curve developed by the department, you see that the smallest value for TC is 10 minutes. This is why the rational method minimum TC is 10 minutes. Here's a list of various Chapter 9 BMPs that can provide stormwater quality treatment. These BMPs are considered GI, which is required to be used to meet the stormwater quality control standard. Note that Chapter 10 and 11 BMPs, which are not listed here, would only be eligible to meet the stormwater quality requirement if a waiver of variance from NJAC 7:8-5.3 was granted. The BMP manual is designed to help the reviewer identify the design criteria that must be met for a proposed BMP to merit the approved TSS removal rate. In addition to the TSS removal rates, there are phosphorus and nitrogen removal rates associated with almost every BMP in the manual. This information is in Chapter 4, which is currently being updated. As seen in that table on the previous slide, not every BMP is rated for 80% TSS removal. Sometimes a series of BMPs are used to meet that, or the more stringent 95% rate for projects discharging within a riparian zone. So when a combination of BMPs are used, justification for the placement order is needed according to the hierarchy seen here. The reviewer should verify that two of the same kind of BMP are not used in series, as the down gradient one will not be as effective. Nutrient removal is required for all major developments. Some BMPs have nutrient removal capabilities, but the best way to handle nutrient removal is by source control. As mentioned earlier, water quality BMPs must be designed in accordance with the BMP manual. Alternative designs may be used, but these designs must be submitted to the department for approval. So in summary, when conducting a water quality review, the reviewer must, one, ensure BMPs used on site meet the stormwater quality standard and are from Table 5.1, are adequate to achieve the required TSS removal rate, and are designed in accordance with the BMP manual. Two, ensure that stormwater runoff that requires water quality treatment is being treated. And three, ensure that a deed notice of the stormwater BMPs used on site is submitted for approval and recorded in the county clerk's office prior to the start of construction. So there are some general design criteria that apply to all water quality BMPs. All BMPs must drain down in 72 hours unless they're designed as water features. All infiltrating BMPs must have a minimum 2-foot separation from the seasonal high groundwater elevation, and underdrain GI BMPs must have a 1-foot separation. Here are the most commonly used water quality BMPs. So every BMP in the manual has a summary page or pages. This is the page for small-scale infiltration basins. The paragraph at the top describes how the BMP functions to remove pollutants and lists the TSS removal rate. The table shown below, the description, lists whether a BMP can be used to meet each of the design and performance standards. As mentioned previously in Module 1, the green leaf denotes if a particular BMP meets the definition of GI, and any design type that does not qualify for this use will be so noted. If there is a TSS rating noted across from the gold % sign, that means the BMP is rated for that TSS removal rate if all of the design criteria are met, including there being a maintenance plan. Notice the design summary tables are now shaded different colors, and the chapter titles are green for Chapter 9, blue for Chapter 10, and black for Chapter 11. The footers are similarly updated. This is to make the amended BMP manual chapters addressing BMPs more visually distinctive from the previous version. Small-scale infiltration basins are an extremely common BMP for water quality. Small-scale infiltration basins achieve the 80% TSS removal rate and may also be used to meet the stormwater quantity and groundwater recharge requirements. Under the current rules, only the volume generated by the water quality design storm may be infiltrated unless specific cases allow for the infiltration of larger storm events, as previously noted. That means there should be one or more orifices or weirs in an outlet to discharge larger storms. This type of basin has additional design criteria in the chapter and also references the detention basin chapter because studies have shown that frequent inundation during larger storms reduces the ability of the basin to infiltrate runoff due to groundwater mounding impacts, which leads to impaired basin function or even failure. And a failed or impaired basin will require retrofit or major maintenance. During your review, you must check that the minimum thickness of the appropriate sand is present and check that the basin is not used as a stockpile location during construction. Look at the existing grading plan or figure out how heavy equipment is going to clear this portion of the site. Make sure there is anti-compaction language on the plans as well as the as-built soil testing. Small-scale infiltration basins designed for water quantity must have an outlet structure. The reviewer must also not see any underdrains or liners in the design of or any topsoil vegetation in the landscape or planning plans. There must be no standing water in the basin 72 hours after precipitation stops. So here's an example of two infiltration basins. The top one is functioning correctly. The bottom one has ponding at the inlet locations, and there's a lot of vegetation established. The outlet is over on the far right of the vegetated basin. This is a pretty big basin, so one question is, how will compaction from vegetative maintenance impact the ability of the basin to infiltrate? Additionally, vegetation is breaking down in standing water, and it forms a biofilm that can cover the sand layer and greatly reduce the basin's ability to infiltrate. So bioretention systems provide more variability to address the rule requirements and are very commonly used. Shown here is the summary page from the BMP manual for the chapter on small-scale bioretention systems. Small-scale bioretention systems rely on healthy, dense vegetation, and the type of vegetation and the thickness of the planting bed determine the TSS removal rate. Rain gardens are a type of small-scale bioretention system and are encouraged under the new rules. There are even types with under drains to help facilitate drainage. Small-scale bioretention systems have specific requirements regarding the depth of the planting media and what planting media consists of. This planting media is designed to support dense vegetation, but also convey stormwater. Notice that the composition of inorganics is measured by volume, but the organics is measured by weight. Small-scale bioretention systems also have specific requirements in regards to stormwater quality depth, bottom slope, and density of vegetation, which can all be found in the BMP manual. The reviewer must make sure that this criteria is met for any bioretention system that is being proposed. So in general, all infiltration type BMPs have specific criteria associated with them, and reviewers should be sure that the criteria is all being met. Reviewers must check that the soil permeability was tested and a factor of 2 was applied to any tested permeability rate. And infiltration BMPs may have a design permeability between half an inch per hour up to 10 inches per hour. When we get into the groundwater mounding analysis, which you can also read about in Chapter 13, you'll see that infiltrating stormwater causes a temporary and localized rise in the groundwater table. If this rise is great enough, it can slow down the rate of infiltration so that the BMP does not drain within 72 hours. This means the basin must be enlarged or retrofitted, and that's why it's so important to make sure the soil testing is done correctly and that the seasonal high water table is properly located. And lastly, when reviewing infiltration basin designs, make sure that the anti-compaction language...
This is Damian Friebel.
Yes. Sorry.
Not at all.
Make sure that anti-compaction language is present along with post-construction soil testing. It would be helpful to include the drain down information in the maintenance plan checklists and logs so that it's easy to find in the future during maintenance activities.
Sure. Yeah, you're constructing a driveway in the DRCC area.
So thank you for your attention. Here's our contact information as well as the contact information for the Bureau. Please don't hesitate to contact us if you have any questions. We'd be happy to help. So up next is part 2 of how to review a project presented by Chang-Yi Wu.
I think we would have a 5 minutes short break before I go to the next presentation. So we probably come back around 2:03, 2:05. Thank you.
Okay, I hope everyone is ready to move on to the second part of the module. We'll wait just a moment for Chang Yi, and we'll get underway.
Welcome back to the presentation. My name is Chenny. I'm going to go over more about how to review a project, part 2. The goal of my presentation is to learn how to review the BMP for compliance with the design criteria in the BMP menu and calculation the detention time of the detention BMPs, and then how to review the safety requirements. And also I'm going to address a little bit about MTD design and also the groundwater recharge spreadsheet. And continue Manish and Anthony's presentation regarding the infiltration BMP. Here's one example of modeling a small-scale bioretention system. This example is an excerpt from example 3 in chapter 9.7. And this project is located outside the coastal plain. There's the background of this project. So the step 1 is to calculate the runoff volume and peak flow rate by using NRCS method. Remember that for the runoff volume, it can be only calculated by NRCS method. So the volume and the peak flow rate is on the slides. And then step 2 is to sizing the pretreatment. Remember that for the small scale BMP, GI BMP, that if you want to utilize the exfiltration in the routing, you have to have a pretreatment. And in this case, MTD is used for pretreatment by following the MTD certification later. And we will address the MTD design later. Then step 3 is run the routing calculation. Oh, sorry, I kind of ahead the one slides. So that's the next slide. Step 3 is to run the routing calculation with infiltration. Then the infiltration area is the initially set up for this case is 600 square feet. And then because this BMP, we have the design size slope is 3:1. So the size of the surface area and the dimension of the basin at different heights can be calculated accordingly based on the slope. And the exfiltration rate is half of the tested saturated hydraulic conductivity of the most restrictive soil layer, as described in chapter 12. And for this case, in the example 3, we said that the condition is that the tested conductivity rate is 2 inches per hour. So we use 1 inch per hour in the calculation. And just a note that the area on the side slope cannot be used for exfiltration. So we have to use the 1 inch per hour times the surface of the size of the bottom to to calculate the infiltration rate in CFS. And continue that the calculation is that you have to adjust the height of the first orifice to result in a water depth that can only allow infiltration of the water quality design stone. So by trial and error, that is 0.98 feet. And please note that there's a maximum water depth in each chapter of BMP design manual. So you have to look into the requirement. And the runoff volume discharge through exfiltration is 939 CFS. Sorry, that's a cubic feet. And then the drain time is the discharged volume through the exfiltration divided by the exfiltration rate. There is 18.78 hours. And the next slide shows the a screenshot of the modeling from HydroCAD. And you can know that we have the exfiltration rate in the calculation is that the routing is discard, and there's 0.01 CFS. So next step is check the separation from the season high water table, and from the configuration that the lowest point of the basin is 3 feet below the existing ground level, and the season high water table is 8 feet below the existing ground level. So the season high water table is 5 feet from the lowest point of the basin. So it's meeting the requirement. And after checking the separation requirement, next step is to check the groundwater mounding analysis, whether there would be a adverse hydraulic impact. For the groundwater mounding analysis, we utilize the groundwater mounding analysis hand-touch spreadsheet. It will be shown in next slide. And for that, the infiltration rate in the spreadsheet, you should use the design infiltration rate, that is 1 inch per hour for this case. And the horizontal hydraulic conductivity for this case is 1 times the recharge rate, 1 inch per hour, as the project is outside the coastal plain. If it's inside, you have 2 times 5. Then use the drain time calculated in step 3 as the duration of the infiltration, and use have the basin dimension calculated in step 3 as the input for X and Y. So here is the output screenshot of the spreadsheet, and from the result, it shows that the mounding height is 861 feet from the water table, and the season high water table is 5 feet below the lowest point of the basin. So the mounding will reach to 2.139 below the lowest point of basin. So in this case, the mounding will not have an adverse impact to the basin. But you may want to also check whether nearby structure or underground structure will be affected by the mounding curve. So you have to check whether the curve and the range of the mounding. So the next topic I would like to talk about is the extended detention basin. The extended detention basin is a BMP commonly used for water quality and quantity treatment, but not for groundwater recharge. But under the amended rules, the extended detention basin only can be used if a waiver or a variance from the green infrastructure requirement from the NJAC 7 Con A is obtained. And under that circumstance, extended detention basin may be used for quality and quantity as they do not meet the definition of GI. So for a detention basin, we have the a specific term is that the detention time. The TSS removal rate is based on the detention time, and the definition of detention time is that the time between when the maximum storage volume is achieved to when only 10% of the maximum volume remains, and use water quality design stone for the calculation of the detention time. And here's the curve for the detention time that in our chapter, and that the you can see that the minimum detention hours should be 12 hours, and the maximum is 24 hours, which means that even you have the extended detention basin that is more than 24 hours, have the detention time is more than 24 hours. The basin can only be credited for 60% of TSS removal rate. And now we are going to give you an example for the detention basin design. For calculation of the detention time, the most important information is that the routing showing the runoff volume in the basin and the time. The different hydraulic and hydraulic modeling software may have different format for the routing. Here's one example of the volume versus the time routing. And you can see the runoff volume starts at 0 when the time is about 0.3 hours. You look for the highest value in the routing table, and it's 0.83 acres feet at 2.1 hours. And next, so the next step is to calculate the 10% of the maximum volume. In this case, 10% of the maximum volume is 0.83 acre feet. So that is 0.00832 acre feet, and we have to go back to the routing table. Then check that the routing table, and you can find that it's between 7.8 hours to 7.99 hours that the 10% volume happens. So the detention time would be the time between the maximum to the 10% of the maximum. So the detention time is 15.75 hours. So use that 15.75 hours. Then you go back to the curve, and then the TSS removal rate is around 47%. Next topic is weight pound. Weight pound is similar to the mechanism to remove the suspended solid is similar to detention basin. But under the new BMP menu, we and the amended rules, there are two types of weight pound. First is GI weight pound, and the other one is the non-GI weight pound. The difference of the different weight pounds is that the GI weight pound, it has to be designed to maintain at least a 10-foot wide area of native vegetation along at least 50% of the shoreline, and also include a stormwater runoff retention component design to capture the stormwater runoff for beneficial use, such as irrigation. And for the GI weight pound, it can be used for water quantity, but if you want to use the GI weight pound for water quality, then you have to receive a waiver of variance from 7 column A-5.3. and the design criteria is described in BMP chapter 10.5. For a non-GI wet pond, it doesn't have the requirement for those vegetation area and also the beneficial reuse. But when if you want to use the wet pond for water quantity and water quality, then a waiver or variance is required. And it's described in BMP chapter 11.5. And note that the wet pond cannot be used for groundwater recharge. And in order to receive the TS at removal rate, then you have to design the wet pond in accordance with our DEP BMP manual. And also that the minimum, there's a minimum drainage area, 20 acres for the wet pond, unless you have the groundwater budgeting balance. And also it needs a minimum 0.25 acre of permanent pool or surface area. And you need to have a permanent pool that can store the water quality design storm volume. And that the soil need to be very low permeability rate, or you need an impermeable liner underneath the pond. A wet pond's TSA removal rate is determined by the ratio of the volume in the permanent pool to the volume of the water quality design storm volume, and also additionally the extended detention time provided by the wet pond. And the detention in the wet pond is same. The detention time in the wet pond is same as the detention time calculated in the extended detention time. And but difference is that the curve shows different curve for the wet pond. And here is the curve. And you can see that the lowest curve is that the wet pond that without extended detention time. And you can see the curve is based on the ratio of permanent pool volume to the stormwater quality runoff volume. And then the three curve above are the curve for a wet pond that designed with different detention time. And you can check those curves and the calculation in the BMP chapter we just mentioned. And we are not going over another calculation for the wet pond of the design because that would be similar to the design of extended detention basin. There's an example in the BMP menu, and you can check it. Next requirement is the safety requirements. And here in our stormwater management rule, that there is a SCAP provision. It needs the safety ledges, and it requires for the basin have a permanent pool of water greater than 2.5 feet. So wet pond is most likely would have need this safety requirements. And also it requires 2 steps. The first step, each step need to be 4 to 6 feet wide, and first step is 2.5 feet below the permanent water level, and the second step is 1 to 1.5 feet above the permanent water level. And next topic, I want to talk about the design of MTD. Mr. Dick McGee already talked about MTD, and I want to emphasize some calculations of the MTD sizing. And there are 2 kinds of MTD. Mr. McGee already mentioned that's GI MTD and also the non-GI MTD. And he has already mentioned that the MTD that you want to use for meeting the stormwater quality design standard, performance and design standard, that has to be certified by the NJCAD and verified by NJCAD and certified by NJDEP. And sizing calculation, you have to follow that in the certification letter. And for the GI-MTD, this is a new requirement for the GI MTD. There is 2.5 acres for the maximum contributory drainage area. And the MTD design must follow the design criteria and use only models listed in the certification letter. And there's a maximum treatment flow rate in the letter you have to follow. And also the stormwater treatment unit should be installed using the same configuration reviewed by NJCAD and size in accordance to the design criteria in the certification. So Mr. McGee mentioned that if there is only one inlet into the MTD and in a direct direction, then you cannot have the two inlets, or you have 90 degree or other degrees of the inlet angle for the inlet. And some MTD that also sized by not only by the maximum treatment flow rate, is also sized by the maximum inflow impervious area. So you have to do the both calculation, then whichever result in the highest minimum configuration, means that you have to choose the higher model the model had a higher capacity. And here the sample language that from the MTD, this one is for the GI MTD, because the GI MTD is treated by vegetation of soil. So there's a language that the minimum vegetative cover in GI is 85%. So so if the maintenance is very important for the GI MTD, if the plant depth of damage more than greater than 50%, I mean that you have to maintain the coverage at least 85% to in order to continue qualify for the assigned TSA removal. And here is the rational method, and the rational method is sometimes being used for sizing MTD. And we mentioned that you should then use the average 0.2625 inch per hour to size. It's wrong. And if you look at the curve that in our chapter 5, you can see that the rainfall intensity, curve for MTD that has a 10 minutes of time of concentration. That is 3.2, around 3.2 inch per hour. So if you use the 0.2625 inch per hour to size MTD, then you underestimate the flow by 80.5%. So for the design of the project, in summary, that the BMP must be designed to meet the criteria in the BMP menu, and if you have multiple BMPs, you can use that in series when necessary. Infiltration BMPs require detailed soil permeability testing. Detention BMP must calculate the detention time to determine the TSA removal rate, and use the intensity, duration, frequency curve in figure 5.5-16 when using rational method to size a pico flow rate. Next topic I would like to talk about is the groundwater recharge. And the rule requires 2 ways to meet the groundwater recharge requirement. One is to demonstrate 100% of the pre-development groundwater recharge is maintained, or infiltrate the difference in the 2-year stone runoff volume. The pros for infiltrate 2-year stone difference is that it is simple calculation. You know that you have the pre and post calculation for the flow, so you will easy to calculate. But the drawback is that it requires larger infiltration structure, and you may have a greater risk of failure because the larger groundwater mounding. And when you use the calculation of the 2-year stone difference, because it's a volume, so you have to use the analysis method. And also, you know that the pre and post construction runoff volume. And then follow all other assumption of NRCS method, and then the curve number and the time of concentration had to match the quantity and quality analysis. And the other method is to maintain 100% of pre-development groundwater recharge. That will require use of the NJ New Jersey groundwater recharge spreadsheet. And then you have to know the pre-development versus post-development land use input, and also the BMP designs. And here is the first page of the groundwater recharge spreadsheet. If you download that from our website, the orange shaded area are for the inputs. The gray area are for the outputs. Let's see the inputs required on the first page. On the left of the page, there are inputs for pre-construction conditions. Right side is the input for post-construction condition. Just know that the infiltration we talk about is not same as the groundwater recharge. I think in the overview, Minesh and Anthony, they already talk about that infiltration is only the process to allow runoff into subsoil. For groundwater recharge, the runoff needs to not only into the subsoil, it has to pass the root zone. So for different soil, there are different depths of the root zone. So therefore, the soil in this spreadsheet plays an important role in the calculation of the annual recharge and the recharge provided by the BMP. So let's look at those input. There are inputs for municipality, pre and post land cover, pre and post development soil, and the size of each different land cover. And as stated earlier, the volume of the groundwater recharge is the runoff infiltrate into the subsoil and pass through the root zone. So the land cover is used to determine how much runoff is infiltrated in the subsoil, and the soil series is used to determine the depth of the root zone. And the spreadsheet would calculate the pre and post development annual recharge. And the difference would be the annual deficit, and that's in the output. And when you review the spreadsheet, the first thing you want to check is the municipality. Sometimes we see that the design engineer, they reuse the spreadsheet for different projects and have the different designation of the municipality, which will incorrectly assign the annual recharge for the area, and that will result a wrong calculation. So the first thing, I always check the municipality. And then we also check the soil land cover, must match the site plan. And sometimes we see that in the calculation of the water quantity and quality, they use one soil, and then in groundwater recharge spreadsheet, they use another type of soil. And also sometimes the soil series are not matching the soil survey report. So you have to check that. And also sometimes the total acreage for the pre and for the post doesn't balance. And also sometimes they are not matching the site plan or the calculation, the acreage that used in the water quality and quantity design. So you just have to check those numbers. And as we talk about in the soil testing presentation, we mentioned that there's a default method for the soil series that you use in the recharge spreadsheet. And here's the table again. So if you don't see the soil series in the soil survey map, then you can use the default value unless you want to conduct the soil testing in the field. And the next, here is the page 2. After you have all the input in the first page, it gives you a deficit. And then you can go to page 2 to have a further input and the design of your BMP. And you can see that from the page 2, there are the VD. The page 1. And for the IMP on the second page is that the targeted impervious area that contribute to the recharge calculation. And the default value is the total impervious surface from the first page. But you can have the partial impervious surface that runoff going to a recharge BMP. You may not have to use the all impervious that will contribute to the recharge. And there would have the auto that the spreadsheet would automatically calculate the output. And there's another important input in the second page. There is the segment BMP. There is the post-development site segment in which the proposed recharge BMP will be located. And as I said, that the soil, different soil, we have the different root zone depth assigned for that soil. So the location of the recharge BMP that being correctly designated is important to get a correct calculation. And if you in the early stage of just the planning of the site, you may use 0 in the segment BMP, but when you have the more clear idea where the BMP is to be, you should put the correct segment number as that you see in the first page. And for the post payment, the segment should be the impervious area of the post development. On the second page, there are another input, other inputs. The ABMP is the BMP area. That is the footprint of the BMP, excluding the slope area. And the DBMP is the BMP effect depth, the maximum equivalent water depth that can be achieved in the BMP before overflow base begins. So if the BMP is filled with stone, then the effective depth is you have to the actual depth times the porosity. For slope BMP, then you can use the average DBMP, then adjust the ABMP to keep that ABMP times the BMP will be always equal to the storage volume. And next input is DBMPU. That is the vertical distance from the vegetated ground surface to the maximum water level. and the other one is the DEXC. That's vertical distance from the vegetated ground surface to the bottom of the BMP. So what do we mean the vegetated ground surface? In this example, that here is kind of one kind of BMP, for example, the Bioretention basin, that the vegetated ground label is on the bottom because the basin has the vegetation on the bottom. So the vegetated ground means the bottom, and if that the vegetated ground is below the water surface, then the dBMPU will be negative value, and that value is the distance between the water level to the bottom of the ground of the basin. And for the DEXC, there will be 0 because the DEXC is defined as the basin bottom to the vegetated ground, so it's the same at the same place, so it's 0. And for another case, for example, this is like infiltration basin. Remember that infiltration basin, we said that it cannot have the vegetation on the bottom of the basin. So the vegetated ground would be the ground above the basin. It's the surrounding ground level. So the distance would be the water level in the basin to the level of those surrounding vegetated ground, and the value will be positive. And the DEXC from the bottom of the basin to the vegetated ground will be the full depth of the basin. And the other example is that if you have the underground infiltration BMP, then the dBMP would be the positive because you have the vegetated ground above, and the water would be label would be the top of the storage area. And for the effective depth, you have to, as we just mentioned, that you have to times the porosity of the fill of the gravel in the storage volume, and the DEXC would be the from the bottom and measured all up to the ground. And here's one example. We quickly go through the calculation, and here is that here is one basin design, and this basin is an infiltration basin, so no vegetation on the bottom of the basin, and the ground level you can see is at the 12 feet, and you have the water quality level is 12.5, but in this case it infiltrates more, so it has the different number, and you can see that we have to use the ground level around the basin as when you designate the dBMPU. And for this case, that the water level is the first orifice, the elevation of the bottom of the first orifice, and is in the elevation of 13.36 feet. And we just mentioned that this meets the first scenario, that the vegetated ground is above, and you can see that on the ground level is not the elevation of the burn, it's the elevation surrounding the basin, so it's a 15 feet. So you have the 15 feet to the water level is 13.36. So you have the 1.64 feet. And for this value, because the vegetated ground is above the water, so it's a positive value. And the DEXC would be the measured from the bottom of the basin to the ground level. And for this one, the effective depth is 1.36 feet is the water for the first orifice, and the volume would be for the first outlet would be 59,400 cubic feet. So from here, you can reversely calculate the BMP by dividing the volume to the dBMP. So there is the input for the groundwater recharge on the page 2. And the one caveat is for the groundwater recharge is that the recharge of stormwater, when you have the high pollutant loading or industrial stormwater exposed to the source material, you cannot recharge those runoff into the subsurface. And all the design have to meet in the design criteria of the BMP in our 9, 10, 11s. And also when you have the BMP designed to infiltrate, you have to consider the adverse hydraulic impact, which is the groundwater mounding analysis you have to see in the report. So we talk about the extended detention basin, wet pond, and have some example for the infiltration calculation. And then have the soil testing. It was used to be Appendix E, now it's Chapter 12. Groundwater recharge, and for next one will be the analysis of the groundwater mounding analysis that will be addressed by Lisa. So here is my information. If you have further questions, you can contact me. So next one will be Lisa for groundwater mounding analysis.
Changyi, we actually have one question that we think your expertise would be best in answering it.
Okay.
Previously, I have had, maybe you could see it in the chat. I don't know if I say it, you hear an echo from me. All right, it says previously I've had issues with the recharge spreadsheet when there was no new impervious. For example, a gravel utility pad. There was no way to route pervious surfaces to a recharge area. Is this still true?
That will be still the case that we have not changed the revised Chapter 6 of groundwater recharge. We are planning to revise the spreadsheet and the menu. So if there are any issues of using the recharge spreadsheet, please notify me and I can incorporate and think of it, how to resolve it, and then incorporate into the new spreadsheet and the menu.
Thanks, Changyi. All right, do we have any other questions? Okay, well, it's 2:46. I think we could take a 3 or 4 minute break and then we'll come back and start the groundwater mounding. Does that sound good? All right, well, if there's no objections, it's 2:47. Let's be back at 2:50 and we'll get right underway. Okay, well, it's 10 minutes to 3, so I think we will get started with the groundwater mounding presentation. And if you have questions, please note them in the chat, and I will do my best to answer them, or Chingy may weigh in as well. So I'm Lisa, and let's get this show on the road. So the material that you'll be seeing is taken from chapter 13, and this was, well, we'll discuss the requirements that are under the groundwater mounding or hydraulic impact section of the rules. We'll go over some of the concepts, one method of calculation, and provide a few quick examples. So the rules require we assess the hydraulic impact of the proposed development on the groundwater table and design the site so as to avoid adverse impacts. Well, first off, what's an adverse impact? Well, when we infiltrate stormwater, the groundwater table, it rises locally, and then it needs some time to spread out before we return to stasis. So when we force a concentrated amount of runoff into one area, we get mounding. Now, this increase slows down the ability to infiltrate, so we can have problems if this increase is large enough to slow down our infiltration rate beyond our 72-hour window, or maybe from repeating this slowing down over and over, we can wind up with the situation of basin failure. Additionally, as this mounding, it spreads out, it can reach adjacent structures such as basements and even septic systems. So let's take a look at an illustration to make this a little bit clearer. So this schematic was taken from the paper prepared by Glenn Carlton from the USGS. And below our basin is the transient mound caused by stormwater infiltrating into the subsoils below our basin. Now I've colorized the saturated zone, whose top is your seasonal high water table shown here. As groundwater infiltrates below the bottom of the basin, we get a localized increase. In order to dissipate, the volume of water under the curve has to move out and down until it eventually gets back to the top of our saturated zone. All right, so how do we calculate this? Well, one method is known as the Hantush equation, and it dates back to 1967. It's a fairly simple method, but it requires computing capabilities such that we might find in an Excel spreadsheet as developed by the USGS. You basically will be entering certain parameters and then clicking a calculate button to enable a macro, and then visually see the results plotted as well as get numerical results. Now, at some point we may get a newer product, but for today we're going to stick with the product that Glenn Carlton developed in conjunction with the department. So this is a screenshot of the Hantush spreadsheet. And I will note that if you've used this spreadsheet that was previously offered, the new one that is on our website is a little bit different. And that's because in March of 2020, when we published chapter 13, we changed some of the variables to be consistent with other terms that we use in stormwater management. So all the calculation algorithms are the same. It's just that the units and the notes for the inputs that are modified to be consistent with the other chapters that are in the BMP manual. So our new guidance, chapter 13, and the spreadsheet, of course, are available at njstormwater.org. So we need to define certain parameters and establish the assumptions for their use in order to run the spreadsheet. So we have to look at recharge rate, specific yield, horizontal hydraulic conductivity, the basin dimensions, our duration of infiltration, as well as the initial thickness of the saturated zone. So let's take a look at each of those inputs. So the first of which is the recharge rate. In the spreadsheet, you use the design vertical saturated soil hydraulic conductivity, and that's 1/2 the tested value of the vertical saturated soil hydraulic conductivity from your soil testing. The second input is the horizontal hydraulic conductivity, and it's rarely tested on a single site scale just for conducting your groundwater mounding analysis. So you will usually use presumptive values, and there's two categories. Basically, if you're in the coastal plain, The horizontal saturated soil hydraulic conductivity is presumed to be 5 times the recharge rate. If your site is located outside the coastal plain, the horizontal saturated soil hydraulic conductivity is presumed to be the same as the recharge rate. So for specific yield, this is what governs how much water the unsaturated zone can store when recharge runoff reaches the water table. So it's the volume of water that will drain from the soil as a result of gravity divided by the total volume of the soil. Now, this is not what you might see elsewhere. For the purposes of this chapter, it is this unique definition. And we have a default value that we use of 0.15 up to a maximum of 0.2, provided you have test data that supports that change. So the Hanter spreadsheet assumes that your BMP is a rectangular shape and that the sides of the BMP are vertical. So we use the width and length of the bottom area of the BMP, our footprint, but since the mounding is highest at the center of the BMP, the spreadsheet uses 1/2 of each dimension as the inputs for the length and width, and they correspond to the X and Y axis respectively. Now, one thing you have to remember is that on for the Hanter spreadsheet, the Y axis is into the page. So, and the Z axis is your vertical. So you just have, once you get that frame of mind, then this starts to gel and make sense. Now, for circular shaped BMPs, you're going to use the radius of the basin as both your X and Y inputs. For irregularly shaped BMPs, you're going to have to convert the shape to a rectangular one that has the same depth of runoff, and then make a best fit to the original shape. I know it sounds a little weird, but we do have some examples. I won't be covering all of them today. If a BMP is designed with slope sides, you're basically going to use the bottom footprint as the length and the width of the BMP and use the total volume of the runoff to be infiltrated divided by the area of the bottom footprint to calculate your duration of infiltration period. And I'll get to that in just a moment. So the initial thickness of saturated zone is another input parameter, and we use a default value of 10 feet. And it's not the thickness of a large regional aquifer. It's the distance from the seasonal high water table to the first hydraulically restrictive layer. So the last one, or near the last one, is duration of infiltration, and it's the time, obviously, of infiltrating our runoff volume through the BMP. We're going to use the recharge rate as the input, and our maximum value is 72 hours. So what you have to understand is that the input values can influence the results. The maximum mounding height decreases when these inputs increase. So if horizontal hydraulic conductivity increases, specific yield, or initial thickness of saturated zone, your mounding height decreases. And you cannot just take credit or take result from the spreadsheet as it appears. You have to check it against the physical constraints of your design. So if you get a resulting mounding height that's higher in elevation than your basin bottom, you're not going to get an artesian condition. It just means that the recharge rate is adversely impacted by a reduced hydraulic gradient. So that means you're going to have to run the spreadsheet again, but using a smaller recharge rate and a correspondingly, meaning proportionally longer duration of infiltration. So this equation represents that proportionality. Volume of runoff to be infiltrated is the duration of infiltration period multiplied by the infiltration area and multiplied by your recharge rate. All right. On the other hand, if your mounding height touches the bottom of the BMP, infiltration is also going to slow down the rate of infiltration. But in this case, you can actually stretch the duration of infiltration period while decreasing the recharge rate to spread the volume over a larger area, and you'll be able to use a shallower depth. So I think we really need to do some examples to kind of make sense of all of this. So I just have two. There were more, but they're actually straight out of chapter 13, which in the interest of time, you can go through, and there's some more complex ones as well. And additional examples in chapter 5 actually include a groundwater mounding analysis as part of the calculations presented. So our first scenario is no adverse hydraulic impacts to groundwater, and then the second one will be a unique adverse hydraulic impact and the adjustments that we would have to make. So for the first example, a major development is located in the coastal plain, and it proposes an infiltration basin whose bottom footprint measures 50 foot by 50 foot to infiltrate 5,000 cubic feet of runoff generated by the water quality design storm. So we know that for this problem, the maximum depth of ponding water, or runoff, I should say, accumulated is designed to be 2 feet. Soil testing is performed in accordance with chapter 12, and that testing shows that the seasonal high water table is 7.5 feet below the 6-inch thick bottom sand layer of our basin. Our tested soil permeability rate of the most restrictive soil horizon below the basin is 4 inches per hour, and there are no nearby underground structures present. So what do we do with this? Well, we start, first off, our soil testing provides our results in inches an hour, so let's use hours for our time values as our unit of measure. We're going to divide the volume of runoff to be infiltrated by the product of the infiltration area and the recharge rate. And then we have to remember that our recharge rate is 1/2 the tested infiltration rate. So therefore, when we go through all of this, the duration of infiltration period is calculated to be 12 hours for this example. So I just made a table of the inputs, and they're just organized to follow the order that they're in the Hunter spreadsheet. So recharge rate is first, and if you're using an older version of the spreadsheet, you would have to convert it 2 inches an hour to 4 feet per day for the older version. So that is our R value on the top line. Specific yield, we will use the default of 0.15. The horizontal hydraulic conductivity is 5 times the recharge rate since we are located in the coastal plain. The duration of infiltration period we calculated in step 1, and in this case we would divide by 24, obviously, to get the number of days if we're using the older spreadsheet. Now, T is less than 3 days, so we're fine. And we use the default value for the initial thickness of saturated zone of 10 feet. And you put them all into the spreadsheet, and then you, this is where the gold section of the spreadsheet is for the inputs, and just so that this is what it looks like when you use it. And after you enter in those values, you have to click the blue bar, and then this will do its whole thing and generate results for you. All right, so the results will show in the red cell in row 16. The maximum height of groundwater mounding that is represented by the variable delta H max. And in this case, it is equal to 6.07 feet. All right, and that's what will occur at the end of the duration of infiltration period. Now, I've superimposed a symbol representing the bottom of the basin, since the seasonal high water table, which in the spreadsheet is always set to 0 here. All right, it's 7.5 feet below the bottom of the sand layer. The temporary elevated groundwater table will not reach the bottom of the basin, so at the center. So therefore, the assessment shows no adverse hydraulic impact. So had the height of mounding been high enough to intersect the bottom of the basin, it would mean that the mounding would interfere with the infiltration capability of the basin, and we would have to run a new model or a trial that would involve increasing the basin footprint to spread out the volume of runoff being infiltrated. Now, that would result in a lower depth of stormwater runoff in the basin since our volume is fixed, and the duration of infiltration period would then have to be recalculated before we rerun the spreadsheet with our new parameters or new values. So since the footprint area is in the denominator, you would see that the duration of infiltration period decreases proportionally as the area increases. If you click on the dark blue recalculate now button and the results show delta H max is larger than the distance from the seasonal high water table to the bottom of the BMP, you won't be able to tell just by looking at the graph. What has happened, all right, is that the temporary elevation in the groundwater table located at the center line of the basin and above the seasonal high water table is intersecting and exceeding the elevation of the bottom of the sand layer. So therefore, it's interfering with the infiltration capability. So this doesn't mean that groundwater will mound off in real life like this. All right, it means that there'll be a reduction in the ability to infiltrate, meaning it will take the BMP longer to drain. So we have to adjust the basin design to reduce this impact. And like I said, we'd have to adjust our parameters and run the spreadsheet calculation again. Now, we would have to reduce the value of R, but we don't know exactly how much it will slow. But a good start is, say, reduce it by 50%. Now, in such cases, we don't make any changes to the horizontal hydraulic conductivity since it's not affected by the reduced hydraulic gradient in the vertical direction. The duration of infiltration period has to be proportionally adjusted though, and that has to reflect this slowing down. So we would double the initial value for T if we have R. Remember, we don't know the exact rate that R will slow down to, but even if it is slowed by half, we're going to check that the mounding for a value of T that is within our maximum allowable time frame. So this is what we mean by stretching the infiltration period. Anyway, we recalculate and check the results to see if our new delta H max is less than the difference between the seasonal high water table and the bottom of the BMP. And you could try this perhaps one more time with a little bit longer T, as long as R is proportionally reduced. And if that doesn't work, then you're going to have to check with Chapter 13 for an example of changing the dimensions of the infiltration area and do a whole nother set of models. But that's it for how the spreadsheet represents your adverse impacts. Let's go on to our second example. So we're going to look at a dry well, and all right, so I said an adverse impact. So this one shows that even a small BMP can cause one. So a site is located outside the coastal plain. A 7-foot high by 5-foot diameter dry well is proposed to store and infiltrate 137.4 cubic feet of roof runoff from a single family home for the water quality design storm. So the house has a basement floor located just above the groundwater table, and the edge of the dry well is 10 feet away from the house. The soil testing, of course, was performed in accordance with Chapter 12, and our seasonal high water table was found to be 2 feet below the bottom of the dry well. The tested soil permeability rate of the most restrictive soil horizon below, it says basin, but we mean dry well, it's 4 inches an hour, and we calculate the duration of infiltration period, and in this case we plug in all of our values and we get T is equal to 42 hours. So it's less than 72. So okay, we can get started. So 1/2 of our tested infiltration rate is used for our recharge rate. The specific yield is the default value. Now we're outside the coastal plain, so the horizontal hydraulic conductivity is the same as the recharge rate. And we calculated the duration of infiltration period to be 42 hours, and we use our initial thickness of saturated zone of 10 feet. So the results show that the maximum height of groundwater mounding, 1.11 feet, that occurs at the end of the duration infiltration period at the center of the dry well. The temporary groundwater mounding does not encroach upon the bottom of the dry well, which I've superimposed here, where had it done so, it would have impaired infiltration and we would have a negative impact. However, we have to remember that we have to check the impact to adjacent structures. The vertical axis, again, is at the center of our BMP being analyzed, and the mounding curve is symmetrical on both sides of the vertical axis. So our basement is 10 feet away from the dry well, from the edge of the dry well. So that's 12.5 feet to the left of the center of the dry well. So I've scaled that out. All right, and drawn that here. And the spreadsheet indicates that the water table is also temporarily raised approximately 0.4 feet at the basement wall location at this point. So that is 0.4. Okay, and so that is an adverse impact that is prohibited by the rules. So therefore, we may have to move the dry well further from the building to avoid the adverse impact that we will cause by the proposed infiltration. Now, in accordance to the with the USGS paper, an increase of 0.25 feet or less is an acceptable depth for underground structures to be temporarily affected by groundwater mounding. So the mounding height at 20 feet from the dry well is just less than that. So it is reasonable to locate the center of the dry well that far away from the building to avoid our adverse impact. But this example is the one that shows even a small infiltration BMP can have an adverse impact on nearby underground structures. So that is basically what I have for the examples. There's a lot more, as I said, in chapter 13 and also in chapter 5. So at this point, I will ask if there are any questions. Mr. Moderator, do we have any?
We have one that just came in.
Oh, yeah. Okay. All right.
Here you go. If mounding impacts basin bottom and before basin modifications are considered, can the evaluation then be based upon a 72-hour duration of infiltration?
You just have to use the proportionality, the equation, to be able to change. If you're going to increase your T, you have to make changes to your R value that are proportional. And you can try that to see if, all right, if it took 3 days, would there still be an impact? So yes, you can make that change. Chang'e, we have another question about specific yield for using a value of up to 0.2 with appropriate tests. What tests are needed for that, and are they detailed in chapter 12? I don't remember seeing them, but
yes, there's a test in chapter 12. We point to the NRCS method there, laboratory manual. There's a specific method for calculating the specific year. But we received comments regarding that not every soil lab is doing that kind of test following the NRCS manual. So we will review it and then see how we can find another method that to do the specific year. But right now, there's a method you can look up chapter 12. We have the information about how to test it.
There's another question here. If we are not in coastal plain and can collect 2 permeameter samples for both vertical and horizontal permeability, is that acceptable to use as input to the hand touch?
excuse me. I have to bring up chapter 12.
Lisa, you mind if I jump in and handle this one?
That would be great because I'm about to lose my voice. Thank you.
Sure. Well, the question is specifically, can you grab a 2 permeameter sample and determine the horizontal hydraulic conductivity? And the answer is no. That's for determining the vertical hydraulic conductivity.
Ooh. Okay. Do we have any do we have any other questions at this point? I think, I know that the agenda showed that we would jump right into the quiz, but actually, we are going to take a few minutes to address some other issues. Gabe, there's an additional question that ties to the immediately previous question.
Right. So the tube permeameter is not a test that can be used to determine the horizontal hydraulic conductivity, no matter how you insert the tube. It's just not a test that can determine that.
Thank you.
All right. So we have a couple of clarifications before we get into the quiz. I don't know which one you guys want to handle first.
I think that I wanted to address any confusion that we may have had. I think it was on day one when we were talking about the homeowner responsibility for maintenance of stormwater management facilities. So I'm right now, of course, it was a week ago. So I'm just gonna start and, or Gabe, if you want to start, that's fine. Just explain what the exact requirements are so that we don't mislead anybody.
Well, sure. The exact requirement is that an owner of a single property in a residential development cannot be assigned maintenance responsibility for any of the stormwater BMPs that are approved as part of that major development, unless that person happens to own the entire residential development. But when we say entire residential development, that's talking about a residential subdivision, like they would own the entire thing and they're leasing the properties to someone else. It's really not a scenario where you're going to come across very often when you're talking about homeowners. Maybe in a scenario where you have a single apartment building or something, there could be one owner of the whole entire thing. But generally in a residential subdivision, you're not going to see that, which means that individual property owners can't be assigned maintenance responsibilities. Now, when we're talking about maintenance responsibilities for the basins, of course, they can still have whatever other responsibilities come with their property, but they can't have maintenance responsibilities for the basin. Now, Nancy, is there somewhere specific that you think we were vague or unclear that I could help clarify?
I thought that there were some questions last Tuesday about the time frame when the basins were built, and I don't know if anybody that's on now had those questions.
Okay, well, I could start addressing that. So certainly what I just said is based on what our rules are today, right, and what they have been since at least 2004. If the basin was constructed prior to that, it could be a little trickier. You have to look at what rules and regulations governed the construction of the basin at that time and what was legal at that time. I don't know what every individual stormwater control ordinance looks like now, and I certainly don't know what they looked like in 1990. But even as far back as 1990, we had a model ordinance. The department had released a model ordinance, and that model ordinance prohibited assigning the maintenance responsibilities to individual homeowners in a residential development. So if your ordinance followed our model in 1990, it would have even been prohibited then. But again, that comes back down to what legal mechanism did you use to approve it at the time of approval. If there was obviously no MS4 program in the state at that time, so there were no requirements from the MS4 program on the municipalities, but if you had adopted our model ordinance, you still have to follow the requirements of your ordinance that was in place. You can't, you couldn't approve something that clearly violated your own ordinance. So it could be very tricky there. It depends on really what you adopted. So you'd have to look back at what ordinance was in place at that time.
Gabe, we have a question here. If the major development involves a 3-lot residential subdivision where stormwater management for each lot was designed to be contained entirely on each individual lot, can each individual homeowner be responsible for maintenance of their individual stormwater management systems?
Nope, not unless one of those homeowners owns the entire residential development. And then it could only be that one that owns the entire development.
Question here, what if the stormwater basin was constructed in the 80s and it is stated in the deed the homeowners are responsible?
Well, again, that just comes back to what I said before. What was the township's mechanism to approve that and require that? Was it done through a stormwater control ordinance or something similar they had in place at the time, and is assigning the responsibility to that individual homeowner consistent with the requirements at that time? I think we had a model ordinance, as far as I know, back to 1986. Now, I think the 1986 model, and I'm going from memory here, so I could be wrong, I think the 1986 model did not address this issue, but the 1990 model ordinance did. So you would just look back and see what ordinance did you have, if you can find it, and what was allowable under that ordinance. Probably if it was 1980 something, early 1980s, I think there was probably nothing in place that prohibited it, but still, it has to be in compliance with whatever the local requirements were. So if the locality had a requirement that said you couldn't do that, then of course it wasn't legal to assign it to them. And at this point, they would either have to establish some new legal mechanism for who's going to maintain that, or the township would have to take over the maintenance.
So just to jump in, so at some point, there would have had to been some explanation to the homeowner if it predated our requirements of what those responsibilities were also, or?
Well, I certainly would think so. So of course, we've seen some deeds that just say homeowner is responsible for the maintenance, and then there's no maintenance plan, and there's nothing on the deed that says what the maintenance is. So I don't know how you could possibly enforce that, because there's just no specifics of what they're responsible for doing. So that leaves everyone in a really vague, tricky situation, since the municipality is required for ensuring that the basin's properly maintained so that it can function. And at the same time, the homeowner is somehow assigned responsibilities, but no responsibilities were ever laid out to the homeowner to tell him what he's responsible for doing. I think in those situations, you really have to develop a maintenance plan that everyone can agree to, because otherwise no one knows what their responsibilities are.
Here's an additional question in regards to that. If the BMP is for a single residential lot that is not in a major subdivision, who is responsible for maintaining the BMP?
Well, if it's for a single residential lot and it's not a major subdivision, do you mean it's not a major development? I'll assume that's what that meant. If it's not a major development, it's up to the township to establish who the responsible party for the maintenance is in those situations. It's not governed by our program if it's not a major development. If it is a major development, and say it's one house that happens to have an acre of disturbance or more than a quarter acre of impervious surface, then in that case, the homeowner can be made responsible because they own the entire residential development.
I think that's clear. Here's a question. I guess the requirement to incorporate maintenance plans in the deeds of records will only apply to commercial sites where usually there is one owner, correct?
No. The requirement to have a deed is, the maintenance plan attached to the deed is across the board, residential and non-residential. It's in the stormwater management rules, so it's going to apply to any project that's a major development. If there are, let's say there's a basin on someone's property, right? Or some sort of stormwater BMP, doesn't even need to be a basin. It doesn't mean that that person is responsible for the maintenance just because the maintenance plan is attached to their deed. The maintenance plan would be attached to their deed pursuant to the rules, but the maintenance plan would say in there, the responsible party is the homeowners association, and these are the tasks that they have to undertake. Or would say the responsible party is the township, or, you know, it's whatever developer owns the property. So that is required on each and every deed that contains a stormwater management feature.
I think we already answered this, but so a small minor subdivision creating more than an acre of disturbance or a quarter acre of impervious cannot exist unless a HOA of 3 lots or the municipality is responsible.
Well, nothing mandates that it be an HOA, so it's any legal entity, any permanent legal entity that's willing to undertake the maintenance. But yes, if you're encountering those situations where someone is subdividing lots up, you do need to think about that in advance, because later on you're not going to be able to have those stormwater management systems assigned to the individual owners of those properties. So you should be in the resolution when you're approving that subdivision, including something about the formation of a homeowners association or another permanent legal entity that's going to be responsible for the maintenance of those stormwater features that are going to be necessary when they do the final plans.
Here's another. Are individual dry wells on residential lots included in the stormwater management systems?
If they're used for compliance with the stormwater management rules, yes.
If the individual lots in a subdivision are provided in O&M and it's recorded in the deed with each lot, would this comply?
I guess there's not enough specifics there to answer. It depends what that O&M says. If that O&M manual says the responsible party is the homeowners association, then it sounds like that complies. If that O&M manual says that the responsible party is the individual homeowner, and that's something that you're doing today, that definitely does not comply with our rules.
So last question here. I thought regulations read maintenance plans have to be in deeds if the person responsible is not or something other than a public agency.
It does specifically say something on those lines. Let me look at it. Right. So if the maintenance responsibility is not a public agency, it has to be recorded on the deed. So if it's, I guess if the maintenance is a public agency, they don't have to record it on the deed. So I think the presumption there is that for most situations where a public agency is responsible, it's because oftentimes there isn't a property to record it on. You know, if it's in the right of way of the roadway or something like that. But the rules don't require it if a public agency is the responsible party.
Okay. I think that's about all the time we have for this specific clarification, and it looks like there's no more questions coming in. I believe we had one or two more. Actually, we just had one more question, if we can get to it quickly. It says, we encounter lots that are standalone lots, but exceed the thresholds of 1 acre and 1/4 acre of impervious surface. By definition, this is a major project. There is a single owner, so all BMPs must be maintained by the homeowner, yes or no?
If that is constructed standalone and not part of a larger residential project, then yes, they can be assigned to the homeowner. So if some homeowner has purchased a lot, it's not associated with any residential subdivision, and he's constructing a house on there that creates more than 1/4 acre of impervious coverage, yes, that person can be made responsible for the stormwater facilities that you make them put in on that. But if it's part of a subdivision where they subdivided it up into 20 lots and every single person is just building their own house on there, that's a problem. That really should have a homeowners association in that situation.
Okay. If you guys have any more questions regarding this, please feel free to send us an email and we will respond to those emails and answer your questions. Nancy, I believe we had another clarification.
Sure. I'm sorry, right now I'm forgetting what the topic was.
There's one for the quiz. In the quiz one, that the question regarding the what's the definition of a major development under the MS4 permit, and we have the answer B, all development project that result in land disturbance of 1 acre or more, and also answer C is that all development project that result in an increase of 1/4 acre of regulated impervious surface. And the answer we provided was C only. And but
C only,
the
Cheng.
definition in the MS4 permit, it says that major development means any development that provides for ultimately disturbing 1 or more acres of land, and any additional development defined as a major development by a municipality's stormwater control ordinance. So if a specific municipality in their SCO have the definition of additional definition that including a 1/4 acre of impervious surface, regulated impervious surface, or other like a motor vehicle service, then that would be their definition for the major development under their MS4 permit. So the answer C could be, it depending on what the SCO that being adopted by a municipality. So we just want to clarify that.
Okay.
Okay.
I don't see any
And
questions regarding that. So was there one more clarification?
I thought we were not going to have time to get to them, so I actually lost my notes since we were working on something else, so we can take care of it on Thursday.
Okay.
I just can't find them right here.
Let me bring up the quiz then.
Oh, okay, great.
If anyone else has questions while I'm pulling this up, please feel free to put them in the chat, and if we have time, we'll get to them.
Here, I know you'll switch over for the review portion of it. Charlie, I do see your question and I will answer it. I didn't want you to think that we forgot you. Okay, so we're gonna go back to the agenda and go through quiz 3. And just one sec. So again, we're going back to the training website, and let me bring up the quiz, and it's same as it was before. Here we go. Yeah, and this time you're going to pick quiz 3, and of course, as before, we will score the class as a whole. This is the link here to the Survey Monkey, and I'm going to turn the quiz on. So just give it a moment, and I think we've allotted 15 minutes for taking the quiz. So it's 3:33. We will check back and I don't know, 3:45 and just see how everyone is doing. And then if we have to, we'll go the full 15 minutes. If you finish, you can take a break and just check back in with us at 3:45 to see how much longer we'll be. All right, so if you have a problem taking the quiz, try refreshing your browser and let us know if there's any other issues.
Can you please put the link in the chat box?
Yes, someone is supposed to paste that. Okay.
Lisa, we have someone who cannot access the quiz.
Yeah, I see that, and it always concerns me. Can you try the what is it, Control F5 to refresh your browser? Because I did open it. Hmm. If you can, open a separate window and copy and paste the quiz link into the URL bar for the new window to see if that will work for you as an alternate. That way you stay in the meeting, but you're in another window. Chris, you have your hand raised. Did you see I repasted the link? And Mr. Rogers or Norm, you also have your hand raised. All right, for those of you who are still having trouble taking the quiz, we can send you, I guess, an email version of it and then review your answers with you via email. Is there anyone else with an issue? Norm, are you able to turn on your microphone and tell me what the issue is? Okay, it's 3:46 and we still have about 20 people who need to finish the quiz. I'm seeing 130 people attempted it. So we're going to take 2 more minutes and see how that goes, and then we'll do our review. Mr. Sabatini, we are going to send you a copy of the quiz to take and return to us, and then we'll go over your, any answers with you, just so you have that personal attention. Okay? Okay, good, Norm. I'm going to lower your hand in the settings. Oh, okay. I'm glad you were able to get it, Charles. Let's see. Let's see how we're doing time-wise. Okay, we just have 5 people. We'll give it another minute and then we'll get this thing rolling. All right, Tim, I think we'll start the review in 1 minute.
All right, sounds good.
All right, yeah, because we just have 1 or 2 people are at the end of the answering. So I think we can start the review. And we're only 1 minute over the time we allotted for the review, but we'll be over 5 minutes or so for the day. Hopefully people can stick around. All right, go ahead.
I won't linger too long on the question. Okay, so first question, which one of the following is not a green infrastructure BMP? The answer to that is D, extended detention basin. Extended detention basins are not considered to be green infrastructure BMPs, and you can check out the tables at 7:8-5.2 to see which ones are considered green infrastructure. And Lisa, do you have a percentage on that?
77 got it right.
Very good. When reviewing water quantity calculations, which of the following must be the reviewer check for accuracy? Hopefully you all got that right. Answer is D, all of the above. Obviously, all of these things must be checked for accuracy by the municipal reviewer. And Lisa, how many got that correct?
95%.
Very good. Might be the best yet. All right, which of the following conditions is false when a stormwater BMP can infiltrate runoff from a storm event larger than the water quality design storm? For example, 2-year storm. The correct answer is C. Extended detention basins can be used to infiltrate runoff of a storm larger than the water quality design storm. And Lisa, how many got that correct?
Well, only 40% got that right. So I think we have to go over this.
Okay.
So, right? I mean, C is false because extended detention basins do not infiltrate any design storm. All right, so that is why that one is false. However, we got 21% under A, 28% of people selected B, and 11% selected D.
Okay.
Yeah.
What is required as part of the municipal stormwater management plan to grant variances or exemptions from the design and performance standards? So there's C, mitigation plan. Municipality must have an improved mitigation plan as part of its stormwater management plan to grant variances or exemptions from the design and performance standards. Lisa, how many got that correct?
75%.
That's actually very good. That this is usually answered not so correctly, so
Yes.
we did good changing up the PowerPoints then. How long ago could an impervious surface have been removed and still be counted as existing conditions in the stormwater management calculations? Answer that is D. Removed impervious surface cannot be counted in existing conditions. When determining the existing site conditions for computations, the design engineer is required to use land cover with the lowest runoff potential that has existed on the site the past 5 years. Because removing impervious surfaces lowers the runoff potential, any removed impervious surfaces cannot be counted in existing conditions, regardless of when they were removed. And the percentage correct?
44.
What was the most likely answer?
5 years. Actually, more people picked 5 years than removed impervious surfaces.
Okay. Put that one on the list of things we need to clarify.
Okay. We do have one hand raised. I don't know if this was someone who had trouble completing the quiz. Maria, can you tell us what went wrong in the chat? No. Oh, okay. No problem. Sorry for the interruption, Tim. Go right ahead.
All right, next question.
Yeah.
True or false, if a project has been reviewed by the NJDEP Division of Watershed Protection and Restoration, formerly known as DLUR, the municipality does not have to review it for compliance with its Storm Water Control Ordinance or RSIS? That answer is false. The municipality is required to review all projects that trigger their definition of major development, regardless of whether they were reviewed by the NJDEP Division of Watershed Protection and Restoration or any other regulatory agency. Lisa?
Oh, I'm sorry. 90% got that right. We do have a question on 8. Do we want to wait to the end or do we want to go back?
We can knock it out quick since it's fresh in everyone's mind.
All right. In regards to question 8, what if the site was demolished due to an environmental cleanup as part of a recent fire? You have to use the most pervious cover condition. So, I'm not quite sure I understand what, if there's something to the question that I'm not getting, or, I don't know if Chingy wants to weigh in.
I think we finished. I think we should finish the review, and then if there's any question, people can stay around. We can answer that because we only have 4 minutes and we have many questions to go. Thank you.
All right.
All right. Good idea. All right.
Which of the following would be exempt from the groundwater recharge standard? Answer that is B. Previously developed portions of a site in a designated center. For a site to be exempt from the groundwater recharge standard, it must be in an urban redevelopment area. An urban redevelopment area is defined as previously developed portions of areas in planning area 1, designated centers, cores, or nodes. CAFRA centers, cores, or nodes, urban enterprise zones, or urban coordinating council empowerment neighborhoods. Lisa?
58.
Okay. True or false? Reducing impervious surface on a redevelopment project always meets the water quantity control standard. And so that is false. Reducing impervious surface may help a project meet the water quantity standard, However, compliance with one of the 3 water quantity options must still be demonstrated. Lisa?
85%.
Okay. What method is used to calculate the groundwater mounding height? The answer to that is C, the hand-tush spreadsheet. And that hand-tush spreadsheet is used to calculate the maximum height of the groundwater mound directly below the basin. Lisa?
87%.
Very good. Can an infiltration basin be designed with a perforated underdrain pipe? The answer to that is no. For BMP to meet the criteria of an infiltration basin in the BMP manual, it must be designated to or designed to infiltrate. Therefore, it cannot have an underdrain pipe. Lisa?
56%.
Okay, not great. In what situation can a design engineer average TSS removal rates across sub-areas? The answer to that is C, when runoff from sub-areas converges on the site. Stormwater management rules state that if there is more than one on-site drainage area, the 80% TSS removal rate shall apply to each drainage area unless the runoff from the sub-areas converge on-site, in which case the removal rate can be demonstrated through a calculation using a weighted average. Lisa?
40%.
Yikes. We'll mark that.
41% selected never, and 16% said as long as the total TSS rate is 16%.
When sizing an MTD by the rational method for the water quality design storm, if the time of concentration is calculated as 10 minutes, which rainfall intensity shall be used? The answer to that is B, 3.2 inches per hour. That's in accordance with figure 5.6 in chapter 5 of the BMP manual. And the rainfall intensity is 3.2 inches per hour when the time of concentration is 10 minutes. Lisa?
61%. 30% still use the average.
When can a wet pond be considered as a green infrastructure BMP? The answer to that is C. Both statements above must be met. In accordance with Note D to Tables 5.1, 5.2, and 5.3, only a wet pond designed to maintain at least a 10-foot wide area of native vegetation along at least 50% of the shoreline and include a stormwater runoff retention component designed to capture stormwater runoff for beneficial reuse, such as irrigation, can be considered a green infrastructure BMP. Lisa?
76%.
Okay. So that is the end of the quiz review.
We're 1 minute over. So we just have the one question with regard to question 8. And that question is in regards, what if the site was demolished due to an environmental cleanup as part of a recent fire? The proposed reconstruction will be in kind prior to the fire.
The rule says that if you have any, you have to use the most, the land cover that has the least potential to generate runoff. So if that the site was demolished and the impervious being removed prior to the project going to approval, then those removed demolished impervious surface cannot be credited for the calculation. So the answer is no.
Okay.
I think if you want to retain that the impervious surface that can be credited as under the pre-development, pre-construction condition, then you better have that being not demolished and have the demolishment plan that's being submitted with your stormwater management approval, then they can approve it together, and then you can get the credit for the impervious service prior to the under the pre-construction condition.
That appears to be it for the questions. It's 4:03, so we didn't keep you too far over, but we'll stick around, or some of us will stick around for a few more minutes if you have additional questions. And I will close the room at 4:15 unless we have more questions. So thank you, everyone, and I guess we'll see you Thursday.